Section 4.1, Inverse Functions. This is part 1 of the notes, and we're going to focus in on the one-to-one functions. Let's start by talking about what one-to-one functions are. So here I have a mapping of my domain and my range. So I can think about this as coordinate points. The point 1, 5, the point 3, 6, the point 2, 7, and the point 4, 8. This is a one-to-one function because each of my domain values, each of my x's, corresponds to exactly one range value, my y's, and vice versa. So each of my y's has exactly one x value. This example is not one-to-one because I have two x values that map over to the same y value. So I have the point 2, 7 and the point 3, 7. That's still technically a function because none of my x's repeat. But what we're saying now is to be one-to-one, your x's can't repeat and your y's can't repeat. So here's a formal definition for a one-to-one function. A function f is a one-to-one function if for elements a and b in the domain, so think of those as x values, a cannot equal b implies that f of a cannot equal f of b. So if my two x values, a and b, don't equal each other, then my two y values, f of a and f of b, can't equal each other. Using a fancy logic concept of contrapositive, we're going to kind of flip that and use the definition, if f of a equals f of b, then a has to equal b. So this is the statement that we are going to use to determine if a function is one-to-one. Make sure that's written in your notes. Example 1, decide whether each function is one-to-one. So part A, we're going to look at f of x equals negative 4x plus 12. So to decide if this is a one-to-one function, we're going to show that f of a equaling f of b results in the fact that a equals b. So first of all, we're going to write f of a equals f of b, and I'm going to take that function f. On the left side, instead of putting in an x value, I'm going to plug in a, and on the right side, instead of putting in x, I'm going to plug in b. Now I'm going to subtract 12 from both sides and divide by negative 4. I end up with a equals b. So by the definition that we just applied, f of x is a one-to-one function. Example 1, part B, we're going to do the same thing, except this time we have f of x equals the square root of 25 minus x squared. So I want to focus in on the x squared here. Anytime we're asking if a function is one-to-one, if we see an x squared, we should kind of have a red flag. Because I could plug in, I don't know, 3 and negative 3 into x squared, and I would still get out a positive 9. So what we're going to do here is we're going to prove that this isn't a one-to-one function. So let's use a as 3 and b as negative 3. We'll find f of a, f of b, and we're going to show that they don't, or that they're equal to each other. So if I plug 3 into my function, and I plug negative 3 into my function, I get out 4 both times. That's like getting the points 3, 4 and negative 3, 4. So our function here is not one-to-one because our a and b aren't equal, but our f of a and f of b were equal. Again, anytime you've got an x squared going on, should be a little bit of a red flag that there's probably a number or two numbers that we can choose that give us the same output, 4 in this case, but aren't the same number that we plug in to begin with. Here I've graphed square root of 25 minus x squared, and we see that it's a semicircle, and it doesn't pass the horizontal line test. That's something that's going to tell us whether a function is one-to-one or not. So vertical line test we've done before. We have a graph, we draw vertical lines. If it crosses more than once, then it doesn't pass the vertical line test. Same idea here, but now we're talking about a horizontal line test. So if we draw horizontal lines, if it crosses our graph more than once, then our function is not one-to-one, which is the case of this example here. So formally we say a function is one-to-one if every horizontal line intersects the graph of the function at most once. Example 2, we're going to look at some graphs. So part A, I have a graph on my screen, and I'm asking whether or not this function is one-to-one. The answer is going to be no, because my horizontal line here in red crosses my graph, in this case, 3 times. Part B of example 2, same idea. This time I have a linear function graphed, and my horizontal lines all only cross at most once. So since every horizontal line intersects the graph exactly once, this function is one-to-one. In general, we can say that any function that's increasing over the entire domain or decreasing over the entire domain is going to be one-to-one. Back to this example that we found to not be a one-to-one function, you can see that we're increasing where it's orange and decreasing where it's green. So we weren't increasing the entire time or decreasing the entire time. We have 4 different tests that you can use to determine whether a function is one-to-one. The first one we did in example 1a, where we showed that f of a equaling f of b resulted in a equaling b. In the next part of example 1, so 1b, we used an example to show that our function was not one-to-one. The third test we saw in example 2, where we sketch a graph and use the horizontal line test. And the fourth way that we can determine whether a function is one-to-one is by looking at whether it's increasing or decreasing on the entire domain.